Hello. Okay. All right, we'll go ahead and get started. I'm going to share my screen. And when we left off, I was talking about functional groups. So let's go back to that. And okay, so I'm going to scroll to the section on functional groups. Here we go. Okay, this is where we left off. Alkanes are okay, just a minute, we've got a couple more people joining us. Okay. All right, go ahead and mute your microphones. Okay, hydrocarbons are those organic compounds that contain only carbon and hydrogen. Okay, when I refer to a heteroatom, that's something other than carbon and hydrogen. That could be oxygen, nitrogen, sulfur, phosphorus, chlorine, okay, anything else except carbon and hydrogen. Okay, alkanes are compounds that have only single bonds between the carbons. All of the carbons are sp3 hybridized, okay, which means they're tetrahedral. In cycloalkenes, you have sp3 or tetrahedral carbons that form a ring. Alkenes are those hydrocarbons that have one or more double bonds, carbon-to-carbon double bonds. And at the double bonds, these are connected by sp2 or trigonal planar carbons. We can have cycloalkenes. We can have a CC double bond as part of a ring. Alkynes are those compounds that have a triple bond present. And in the triply bonded carbons, those are sp hybridized or linear. Aromatic compounds will contain a benzene ring. Okay, there's a more extensive definition that we'll talk about next semester. Okay, here are the names of the first 10 alkanes, and you'll need to know the names of these. With one carbon, that's CH4, that's methane. 2 carbons is ethane. 3 is propane. Then we have butane, pentane, hexane, heptane, octane, nonane, and decane. Cycloalkanes have the carbons arranged in a ring. Okay, the smallest ring you can have is 3. 5 and 6 membered rings are extremely common in nature. Larger and smaller rings are less common. Okay, so here we have some examples of alkenes. Okay, and here we have both the IUPAC or systematic name and then in parentheses you have the common name. Industrially, commercially in the United States, many compounds are still known by their common names. Okay, so here we have a couple of alkenes, but-1-ene and but-2-ene. Okay, the number indicates the position of the double bond. Okay, but-1-ene, butane, if you go back to names of the alkanes, that's 4 carbons. The suffix -ene indicates an alkene, and then the 1 indicates that that double bond is between 1 and 2. For but-2-ene, the double bond is between 2 and 3. Okay, so these are referred to as positional isomers. Isomers have the same molecular formula, the same molecular weight, but a different structure. Okay, and then alkynes are compounds that have 1 or more carbon-carbon triple bonds. Okay, the simplest alkyne is called ethyne, or commercially it's known as acetylene. Propyne is also known as methylacetylene. And then, just like with the alkenes, okay, if we have anything longer than a 3-carbon chain, we need to specify the position of the triple bond. So this is but-1-ine. Okay, but indicates 4 carbons. Ine is the suffix for an alkyne, a triple bond. And then the 1 indicates that the triple bond is between 1 and 2. So we have but-1-ine and but-2-ine. Aromatic hydrocarbons, for our purposes right now, we're going to say those are compounds like benzene. These are also called arenes. And although they may look like alkenes, they are classified separately because their reactions are going to be very different. Okay, next we will look at some compounds outside of the hydrocarbons, and we'll begin with compounds containing oxygen. Okay, first of all, we have the alcohols. And these are some examples of alcohols. And we'll cover these various functional groups in depth. Usually a chapter is all about a particular functional group or a few related functional groups. Okay, and alcohol has a general formula ROH. R is some indefinite carbon group, and these are all examples of alcohols: methanol, ethanol, propan-1-ol, propan-2-ol, also called isopropyl alcohol. Okay, they differ from ethers. Instead of ROH, ethers are ROR prime. And you can have cyclic ethers such as furan here. This is diethyl ether, methyl tert-butyl ether, for example. The CO double bond is actually not a functional group. It's a part of several functional groups, but it's called the carbonyl. Okay, so when I use the term carbonyl, that's a CO double bond. Okay, there's several groups that contain this subunit. And here we have aldehydes and ketones. Okay, here we have ketones where the carbonyl carbon is bonded to carbons on both sides. Here are some examples. Propan-2-one, commonly called acetone, butan-2-one, also called methyl ethyl ketone. And here we have a cyclic ketone, cyclohexanone. Okay, if one or both sides of the carbonyl carbon is attached to a hydrogen, then we have an aldehyde. Okay, so this is ethanal or acetaldehyde, propanal, and butanal. Carboxylic acids have this structural feature. They have both a carbonyl and a hydroxyl group on the same carbon. Okay, this one might look like an aldehyde. Okay, if you ignore the OH, but it is actually a carboxylic acid based on how it reacts and its properties. Notably, it's very acidic. So that one actually is a carboxylic acid. Okay, and we'll learn the names of these, especially the systematic names, as we come to the corresponding chapter. But these are just some examples, and their names are given. Okay, these are what are called carboxylic acid derivatives, and we'll cover these second semester. These are all grouped into one chapter. They're called derivatives because they can be broken down into a carboxylic acid and some other functional group or some other compound. Okay, so this one, where we have a C double bond O and a Cl, this is called an acid chloride. Okay, it is also called an acyl chloride. Get the light so you can see that a little bit better. It's also called an acyl chloride. This is actually a more correct name because you can have acid chlorides of other acids. Okay, such as phosphoric acid, you can have a phosphoryl chloride. Okay, an acyl chloride specifically refers to one derived from a carboxylic acid. Okay, so if we replace the hydrogen on the carboxylic acid with some R group, then we have an ester. And here's an example of an ester. This one's called ethyl acetate. Ethers and esters are frequently confused. Okay, the ester has the carbonyl, the ether does not. Okay, then we have what is called an amide or amide. And here we have a nitrogen connected to the carbonyl carbon. Okay, next we'll look at compounds that contain nitrogen. Okay, and these include amines, amides, and nitriles. Okay, we've already seen an example of an amide. Okay, so these are amines. Okay, we start with ammonia, NH3, and then we replace 1, 2, or all 3 of the hydrogens with carbon groups. And these are just a few examples. This is methylamine, ethyl, and ethyl is a 2-carbon branch, ethylmethylamine, and then this is triethylamine. We've got all 3 hydrogens replaced with these 2-carbon branches called ethyls. Here are some cyclic amines, piperidine and nicotine. Okay, nicotine has 2 heterocyclic amine groups. So these are alkylated derivatives of ammonia. By alkylated, we mean hydrogens are replaced with carbon groups or alkyl groups. Okay, earlier we saw an example of an amide. This is what's called a primary amide, where we have two hydrogens remaining on the nitrogen. This would be a secondary amide where we have one hydrogen remaining, and then this is what's called a tertiary amide, where there's no hydrogens remaining. Okay, so this is a primary amide, acetamide. N-methylacetamide would be a secondary, and then NN-dimethylbenzamide would be a tertiary. Okay, so amides are derivatives that result from a combination of a carboxylic acid with either ammonia or an amine. Okay, the difference between an amide and an amine is the carbonyl group. Okay, going back one. Okay, these are amines, there's no carbonyl. With the amides, we have a carbonyl next to the nitrogen. Nitriles will have a CN triple bond. Okay, and these are a few examples of nitriles. Okay, acetonitrile is an important solvent. Okay, here we have propionitrile and benzonitrile. Nitriles are also considered to be derivatives of carboxylic acids, even though they don't look like it. But if you do heat a nitrile with water, either a strong acid or a strong base, one of the products is a carboxylic acid. Okay, before we go on to the next chapter, I have a couple of other functional groups that I want to introduce, and these are the alkyl halides, okay, also called haloalkanes. And an example of a haloalkane would be this one. Okay, this would be, without the chlorine, if we had a hydrogen there, this would be C5H12. That would be pentane, and then I've replaced one of the hydrogens with a halogen. Okay, another example would be this. Okay, where we, again, have replaced one or more of the hydrogens with a halogen. Okay, the halogens are fluorine, chlorine, bromine, and iodine. Okay, and then we will be talking about organic sulfur compounds in this course. And those that have the general formula RSH are called thiols. The older name was mercaptans. Okay, so if you happen to be looking at literature from the 1950s or 1960s, these may be referred to as mercaptans instead of thiols. Okay, sulfur is in the same family as oxygen, so these have some similarities to alcohols. Okay, if we have this type of structure, okay, this is called a sulfide, or, okay, think of the ethers, RO, R prime. They're also called thioethers. Okay, and then there's one more. Okay, this is called a disulfide. Okay, while thiols and sulfides have equivalent oxygen compounds, so does the disulfide, but the difference is this is a stable functional group, whereas this, where we replace the sulfurs with oxygens, this is a peroxide. And peroxides are not stable. Okay, they can explode. Sulfides are an important structural subunit of protein structure, and thiols are one of the groups that is also present in proteins. Okay, next we're going to turn our attention to Chapter 3. And we're going to specifically look at the structure and stereochemistry, or three-dimensional geometry, of alkanes. Okay, in the previous PowerPoint presentation, we went through the classes of hydrocarbons. So I'm going to skip over that. Right, alkanes have the general formula CnH2n plus 2. Okay, where n is some positive integer. Okay, so if we had 15 carbons, for example, we would predict that there would be 32 hydrogens. Okay, that's if there's no rings or double bonds. Okay, because rings and double bonds will reduce the hydrogen to carbon ratio. Okay, this ratio is useful in analysis of alkanes, because if the hydrogen to carbon ratio is smaller than 2n plus 2 to n, okay, that tells us that either rings and or double bonds are present. Alkanes are found in natural gas and petroleum. That's their principal source. The smaller alkanes have very low boiling points. Okay, we talked about intermolecular forces in the last chapter, and the only intermolecular force that's taking place between alkane molecules is London dispersion. And these are pretty weak. So CH4, methane, boils at minus 160 Celsius. Ethane boils at minus 89, and propane boils at minus 42. Okay, so they're all gases at room temperature. And you've got to get them pretty cold to liquefy them. All right, these are some alkane examples. And they're full Lewis structures. We've got methane through butane. This one is isobutane. Okay, it's an isomer. It's also C4H10, just like butane. Okay, here we have the three isomers of C5H12. They're commonly called pentane, isopentane, and this one is neopentane. Okay, to go from pentane to isopentane, okay, we remove one of these carbons on the end, and then instead of putting it back on the end, we put it on the second carbon. Okay, so we have a branch. Then if we take isopentane and then we remove this carbon on the end and put it in the middle, and we've got neopentane. Okay, we talked about a homologous series. Those are groups that differ only in the number of methylene or CH2 groups. Okay, so these four would be a homologous series. Isobutane and isopentane would be a homologous series. Okay, if you take isobutane and you insert a CH2 group here, you've got isopentane. Okay, so these are the smaller alkanes, methane through butane. Okay, this may be a little hard to read, but these are the physical properties. But I want to make some general comments. Okay, these are all straight chain alkanes. Okay, and again, I want you to know the names of the first 10. Okay, it wouldn't hurt to be familiar with these others. So 11 is undecane, 12 is dodecane, you've got tridecane, tetradecane, and so on. Okay, but notice these are a homologous series, so notice the boiling points go up as we increase the number of carbons. So do the melting points. And methane through butane, those are all gases at room temperature. Pentane is the first one that's a liquid. It boils at 36 degrees Celsius, okay, which is about 96 degrees Fahrenheit. Okay, so in a really warm laboratory, this would start to boil. Okay, and then as we increase the molecular weight, again, the boiling points and melting points go up. And then the last column is density. Okay, the gaseous and the liquid alkanes are all less dense than water. Water has a density of 1. And they don't dissolve in water. So if we had something like hexane and we mixed it in a container with water, it would simply float on top. Butane and isobutane are examples of what we call constitutional isomers. They're also called skeletal isomers. And these are defined as compounds that have the same molecular formula, but the carbons are connected differently. Okay, so these are different compounds, even though they have the same molecular formula. They do have a different structure. Once again, these are the 3 pentanes, or 3 isomers of C5H12. When we get to 6 carbons, C6H14, there are 5 possible isomers. And the number of possible isomers goes up rapidly as we increase the number of carbons. And so even with 5 isomers, naming each compound individually is starting to become very cumbersome. And so for that reason, there was an organization called IUPAC that developed a method of systematic nomenclature. IUPAC stands for the International Union of Pure and Applied Chemistry. It is based in Geneva, Switzerland. And besides developing official rules for naming organic compounds, it also has a systematic method for inorganic compounds. IUPAC is the organization that officially recognizes definitions of units of measurement. They also officially recognize the names of elements. Okay, if someone discovers a new element, then it doesn't become official until IUPAC recognizes that. Okay, so in this standard method, which is used internationally, it uses the longest chain of carbons as the main chain. Okay, so going back to our table earlier, this one, okay, these are all main chains. Okay, so it uses that name. And we have a set of rules that we follow to name a compound, even a compound that we haven't seen before. Okay, so we find the longest continuous carbon chain. And we use that name as the base name or the parent name of the compound. Okay, and then you number the longest chain. Okay, beginning with the end of the chain with the nearest substituent. Okay, so we're not required to go left to right or right to left. It's just wherever the nearest substituent is. Okay, rule number 3. We name the groups attached to the longest chain as alkyl groups, and we'll talk about that in just a moment. We'll give the location of each alkyl group by the number of the main chain carbon atom to which it is attached. And then we write the alkyl groups in alphabetical order, regardless of their position on the chain. Okay, so here is one example. Okay, and we've got 1, 2, 3, 4, 5, 6. Okay, the reason that we don't do 5, 6 is actually the longest chain, and this is flexible. Got a model kit here that I can show you. Okay, so we've got these tetrahedral carbon atoms. Okay, and as the model kit accurately predicts, we do have free rotation. So I'll add a few more here. Okay, so 1, 2, 3, 4, 5, 6. Go. And then we need a 1 carbon branch of the third one. Right, so this is that compound, and we rotate it so that it's like this, okay? And we might think that, okay, since this is the horizontal part, that this is the main chain. But the main chain is actually 1, 2, 3, 4, 5, 6. And I'll see if I can zoom in a little bit so you can see that better. Okay. So here we go. This is one. Here's our main chain, and we can freely rotate. Okay, when there are two longest chains of equal length, we want to use the chain that has the greatest number of substituents. Okay, so these represent the same compound, but this would be the correct representation of the main chain and the substituents. Okay, and then we number the main chain. Okay, we number the longest chain beginning at the end of the chain nearest the substituent. Okay, so this is the correct representation. We start here. This is 1, 2, 3, 4, 5, 6, 7. And the substituents are shown color-coded here. One carbon branch like this is called a methyl. Okay, so we've got 3 of these methyls. This 2 carbon branch is called an ethyl. And these numbers represent the positions along the main chain. Okay, so there's a lot of information here. We would name ethyl first because it's alphabetical, comes before methyl. We actually ignore the tri prefix when we're listing these alphabetically. Okay, so ethyl is on the 3rd position. So here's the ethyl. And then we have methyls at position 2, 4, and 5. Okay, so we separate those with commas. Trimethyl because there's 3 of them. And then heptane is the parent chain, which is 7. Okay, so these are the common alkyl groups. Okay, if we remove a hydrogen from one of these alkanes, then we remove the suffix ane and then we add yl. So a CH3 is a methyl. And then ethane, we remove a hydrogen, it becomes ethyl. And then propyl and butyl and pentyl. This is the old name amyl or N-amyl for pentyl. This still has use in commercial products. Okay, so besides methyl and ethyl, we have some variations that can occur with 3 and 4 carbons. Right, we saw the propyl group earlier. Propane is 3 carbons. If we pull a hydrogen off the end, then it's a propyl group. But if we pull a hydrogen off the middle, then it's an isopropyl. Okay, so this would be heptane, 1, 2, 3, 4, 5, 6, 7. And on carbon number 4, okay, this would be a propyl group. Okay, this is our 3 carbon substituent, and we've taken a hydrogen off the end and then connected it. Okay, so that would be 4 propyl heptane. Okay, if we take a hydrogen off the middle carbon, like this, okay, that is an isopropyl. So this is 4 isopropyl. Or isopropyl heptane. And we write this all as one word, no space in here. There is a dash between the number and the first letter.
Could you spell that first word for me? It's kind of blurry on my camera, and I was just trying to see if I could write it down right.
Here?
Yeah.
Okay. Yeah, I'll also write it bigger. Okay, so this is called 4-propyl. Make sure I'm still on screen. 4-propyl heptane. And then this would be 4-isopropyl. Okay, propyl and isopropyl depends on whether you connect it using the end carbon or the middle carbon. Right, then we have 4 different butyl groups. We have the butyl group, where we take butane, we remove a hydrogen from the end, and this is sometimes called N-butyl. This is also called N-propyl. For emphasis, the lowercase n means normal. You don't want to use a capital N because that's nitrogen, and we'll see later on we'll have compounds that have a capital N. Okay, the other way in which we can connect a straight chain, okay, I'm going to skip over this one, and that's this one called a sec-butyl. Okay, again, let's use heptane as our parent. And 1, 2, 3, 4, yeah, so heptane is still the longest chain, and this would be 4-butyl heptane. Okay, if we take that 4-carbon straight chain and instead of removing a hydrogen off the end, we remove one off the second carbon. Okay, so here's my 4-carbon chain, but I've connected it to the second carbon. Okay, so this is called 4-sec-butyl. Straight chain off the second carbon. Okay, and then I have 2 more, and I think we'll be finished for the day. Okay, the other 2, let's go back to heptane. The other 2 are based on isobutane rather than butane. Okay, there's 2 ways of connecting this to the parent. Okay, we can pull a hydrogen off the end. Okay, we've got 9 hydrogens here on the end. Or we can pull this one off the middle. Right, if we pull it off the end, this, my isobutyl group. Okay, that's called isobutyl. So that'd be 4-isobutyl heptane. If we remove it from the middle, okay, this is tert, I'll write it bigger here. This is called tert-butyl, or sometimes you might see it written as just T-butyl. Okay, maybe use your imagination. It looks kind of like a T. Okay, so those are the common alkyl groups. Right, so I'm going to go ahead and close, and I will save this and upload it, and I will see you on Monday.